Hi everyone, I'm Professor McBain and welcome back to Chem 100. And this is Ludwig. Ludwig is going to help us get started with the next topic in our course, which is water purification. All right, let's start talking about water purification. I would say that this is one of the most practical ways that your knowledge about chemistry might help you in your life, right? Because we're drinking water all the time, and hopefully you're consuming purified water, or at least water that doesn't have any of the nasty things that we were talking about last week. So hopefully you find this information useful to you. All right, let's go. So today we're going to talk about several water purification methods, both how they work, but also some advantages and disadvantages to them. One of the reasons why we're talking about several instead of honing in on just one is because there are several ways to get this whole thing done. And how water treatment plants operate is actually by using a lot of these in conjunction with each other, all right? So yeah, you might do some coagulation first, and then sedimentation, and then filtration. But then, of course, your home might be set up with an RO machine. If you find yourself without a whole lot of this fancy schmancy equipment, then you might have to do some fast and dirty distillation instead. If you live somewhere that's got really hard water, then you might also have an ion exchange filter installed. So just to sum this all up, there are lots of different ways that water can be purified, and some of them tend to go hand in hand with each other. So let's start talking about these. So first of all, which would be a microscopic view of water boiling? Now I'm going to give you a hint. If water boils, but then you let that stuff cool back down, is it still water? Right? It might not be liquid water once it's boiled, but is the gas stuff, is that also water? I would say it is. Here's another question. If you boil water and then you stick like a match in the steam that's generated, is that match gonna suddenly go boom? No, it's not, right? So D does not seem so probable. Same thing with C. Even though we don't have all this oxygen and hydrogen, right? Actually, if you've got single oxygens and single hydrogens, they tend to be even more reactive because they haven't formed these diatomic bonds just yet. Now, if you boil water, you can't just make it go away like this, so B is also not correct. So then that really just leaves A. Okay, why am I bringing up water boiling? Because it's going to help us understand the basis of the first water purification method that we're going to be talking about. It's the simplest to understand. It is distillation. Here's the idea with distillation. You start off with some water that is not pure, all right? It's got something in there that you don't want to have. And so then you add heat. Let me get my laser pointer. So then you add heat and you cause that water to boil. So ideally what's happening is that only the water molecules are boiling, and whatever the contaminant is, it has such a high boiling point that it actually gets left behind because this flame is not hot enough to actually cause that thing to boil, but it is high enough to cause the water to boil. So this water boils away, and being steam and gas, it tends to fill up whatever container it's in, and so then it goes through this tube that is now very cool, and right here the water recondenses back down. So then you collect that recondensed water that now has been in gas phase without whatever the nasty things were over here, and then now you've got some purified water. So to sum all of that up in, I guess, chemical equation lingo here, you start off with liquid water that is not pure. Upon adding heat, you cause that water to pass into gas phase, but then travel to a new container, and then once you remove the heat, or in other words, cool it down, then you've got purified liquid water once more. Okay, so there are several issues with distillation, all right, and so one of the big things is that distillation can't remove anything that has a boiling point that is below that of water. So anything that boils at, say, room temperature, like volatile organic chemicals or chlorine, those things are actually going to boil before the water does, and they're going to end up in your collection flask before the boiled water does. And so then you've still got the same issue that you're left with, right? So that's not good. On the other hand, if your starting sample is something like salt water, well, salt has a very, very high boiling point. In fact, salt has a really, really high melting point. It won't even turn into liquid phase before about, I think it's like 1400 Fahrenheit or something crazy like that. So this works as long as you've got, say, inorganic contaminants that have very, very high boiling points, but not for things with low boiling points like chlorine and volatile organics. One of the other problems with distillation is that water itself has a very high boiling point. I mean, it's not very, very high, but it's decently high enough that it takes a lot of energy for you to boil this water, to take it up from 25 degrees Celsius up to 100 degrees Celsius. Okay, so it's not very green for you to be purifying your water with this energy-intensive method. Okay, so and then the other issue is that a lot of energy tends to get released when you are ready for the water to condense back down from steam into liquid water. So not only does it take a lot of energy to start things off, but then you're losing all of that energy and it's going nowhere once you're ending up at the end of this process, okay? And so usually in distillation, you're getting that energy, that add heat energy from burning fuel of some sort, right? And so then we've got this issue of continuing to release greenhouse gases into the atmosphere, and you can see that it's just not our favorite, right? Especially in a sustainability themed class. One way to help counteract all of that, that not green stuff happening is that you can perform distillation on a large scale in what they call a multi-stage flash distillation factory, okay? And so basically what's going on here is that the heat that tends to get removed, all of this heat that's leaving the condensing water anyway, is then contributed to the heat that boils the next batch of water in the first place, all right? So you've got batch 1, batch 2, batch 3, and so then this vapor tends to help warm up the next stage of brine that is getting boiled and stuff. So that's one way to make this a little bit greener, but most of you probably don't have MSFs at home, right? So if you're just trying to purify your own water, this isn't really a good way to do it. But this works if distillation is being used to purify water for, say, a very, very large population, okay? And so there are quite a few places that do use multi-stage flash distillation to purify salt water into drinking water, especially Saudi Arabia and the UAE, and then also Australia, right? All of these places that tend to be surrounded by water and not have a whole lot of their own natural bodies of fresh water available. Okay, that's one method. Another method that tends to be used quite a lot is what they call flocculation. I love this definition of flocculation. A process of contact and adhesion whereby the particles of a dispersion form larger sized clusters. Nice. Yeah, whatever. So what's going on with flocculation is that you start off with small particles, and what's going on is that they are attracted to dirt and ions and some other stuff that you might find in your water that you want to get rid of. And with very, very slow mixing, they aggregate to each other to form larger particles, which just naturally become very, very heavy. And so then they sink to the bottom of your container. And that leaves behind all this lovely fresh water. And so all you got to do is just pour it off. And then all of this gunk at the bottom just needs to be disposed of. Okay. So let's take another look at those polymer flocculants. So this is an example of polyacrylamide, and this is basically the polymer that you use, but not quite in this way. What you have to do is you you copolymerize polyacrylamide with acrylic acid, and then you treat it with a very strong acid in order to deprotonate it, and then basically you get this polymer that is slightly charged. Okay, and we learned last week about charged ions, right? And so you have this polymer which has lots and lots of negatively charged sites on it. So once you dump this polymer into some water that contains, oh, I don't know, metal cations, then they tend to attract calcium, right, at those negative sites. And then the calcium, in turn, attracts soil particles, which tend to be negatively charged, okay? And so the polymer basically helps all of this co-attraction happen so that you can get out any undesired metal ions and then also a bunch of soil out of your water sample. So let's take a look at that flocculation process. So again, you've got these neutral clay particles, but you've also got the polymer that's in there. And so they go into one tank, and just with some slow mixing, you can get those polymer particles to, of course, trap everything, but then with some slow mixing, they'll form larger and larger aggregates. Then they go into the next tank, and there's more mixing, and then they form even larger aggregates, and so on and so forth. They're always forming larger aggregates, the more and more spinning happens, okay? And so then in the next scene, the next phase called sedimentation, basically all that they're doing is allowing these very large aggregates that formed with those polymers to just settle into the bottom of a holding tank, and then it allows all of the fresher water to continue through to the next phase. Okay, so all the sludge forms, and then it is pumped out of the bottom of that holding tank. Then if there are any small particles like that, like these guys, left over, then they can go through some basic filtration through some layers of sand and other fine grit and stuff, and water is just going to sink due to gravity, but any leftover small particles that didn't get trapped by that flocculation business, they're going to get trapped by that sand, just by physical adhesion. All right, let's go back to our PowerPoint. So technically what's going on with flocculation is that it's really a two-stage process. First, you have a coagulation phase, which is where the ionic polymer is capturing any hard water ions and soil, and then flocculation is really where you mix up the particles, the polymer particles, so that they aggregate into those larger particles that can just settle into the bottom of the holding tank. So that's why you might hear me use them kind of interchangeably, but they do go together, okay? All right, so that's flocculation and coagulation. So we haven't talked about the disadvantages to flocculation and coagulation. Really the main disadvantage here is that this anionic polymer, and really any polymer, is prone to breaking down and releasing units of the monomer back. Okay, and so the issue with any polymer releasing its monomers is that the monomers tend to be toxic. Okay, so polymers tend to be organic compounds. If they're large enough, well, if you ingest that organic compound, it's not going to do much to you. But the monomers are small enough organic molecules that they will actually cause some like carcinogenic type of damage. And sometimes these monomers will be present in concentrations as high as 1,000 parts per million. So that's not our favorite, right? We don't want to have dangerous organic chemicals in our water on the order of parts per million. That's a bad idea. So let's move on to our next topic, which is ion exchange. Ion exchange is another system that tends to use this idea of charged polymers or charged resins. Let's see. Let's take a look at this legend. So we've got this ion exchange material. A lot of ion exchange materials tend to also be negatively charged, just like we saw with this, this flocculant, this anionic polymer, right? So this polymer actually has negative charges. So now on this bead, imagine that there are little negative charges all over, okay? And so those little negative charges would be attracted to anything that is positively charged, such as sodium ions, which tend to be which tend to be positively charged. Right, sodium has positive charge. We saw on the last slide as a reminder that calcium tends to be a 2+ charge. This is really hard with a trackpad, you guys. I don't have a pen. And then with magnesium ions also tend to be 2+ ions. There, got some decent stuff, right? So what you'll do with an ion exchange column is that the ion exchange column will actually be delivered to you more like in this phase over here. Oh, yikes. But so they're manufactured with a bunch of sodium ions that are attached to the negative charge sites on the ion exchange material, okay? But your water might have a lot of magnesium and calcium due to being hard water. So the idea here is that as you flow water that contains a lot of magnesium and calcium through, then those metal ions will replace the sodium ones. And so the magnesium and the calcium will get stuck on the ion exchange beads, and then they'll cause the sodium to flow through along with the rest of the water. Okay, so then instead you get out all of this water that is high in sodium content, not necessarily salty tasting, but it just has a lot of sodiums, whereas you originally had flowed through this water that was higher in calcium content and tended to leave all of those nasty water spots on your glasses and so on. Okay, so it just literally, it traps the calcium and magnesium just by these ion beads having negative charge sites to them. Okay, so if you have an ion exchange column or a water softener, right? If you have a water softener system, what you really have here is an ion exchange column. Isn't that cool? So the main disadvantage with ion exchange is really all of that sodium that is being released into your water. I mean, again, I told you it doesn't taste salty particularly, but the problem is that the sodium tends to make other stuff dissolve. Okay, so I don't know if you remember from lecture 5, the lecture 5 series, remember how all of that extra chloride in Flint's water tended to make the iron dissolve? Well, guess what? All of the extra sodium that you could be releasing into your water can make other ions dissolve as well. All right, and so that may not be what you want to be drinking necessarily. Okay, that's enough for this video. In our next video, we're going to be talking about filtration and reverse osmosis. See you next time.